everybody. Welcome to another episode of Master the NEC, as well as Electrician Live, the podcast and video cast series. My name is Paul Abernathy, your host, and today we're going to talk a topic, supply-side bonding jumpers. Now, this was and we're casual today. Okay, got my coffee, got the mic here. Everything's casual today, and we're going to talk about a topic that a lot of people get confused about. And so I had an email that was sent to me that said, Paul, you've sized equipment grounding conductors, you've sized grounding electroconductors, you have a lot of videos on grounding and bonding, and again, that's a plug to my grounding and bonding series that we have on the YouTube channel, as well as some of the podcasts we have on our websites, masterthenec.com. You can listen to all those different podcasts on different topics. I try to paint a visual picture, even though you're hearing it a lot of times and not getting the benefit of the video. And so I talk about a lot of things grounding and bonding, and a lot of examples. And that's a good example for you to watch our service bonding basics video we have out there. Okay, we have a video for that as well. So watch all that. But today they wanted to know, can you give me the down and dirty on sizing supply side bonding jumpers and make it less complicated? So I've got a lot of slides that will tend to try to make it complicated, but I'm going to try to make it less complicated for you, especially if somebody that's in the field and they want to understand the concepts of bonding and why it's important to know what a supply side bonding jumper is and how to size it. So we'll talk about that in this episode and try to keep it as brief as we can. All right. So first things first, we want to understand when it comes to supply side bonding jumpers, we need to know what one is, what a definition is. Now, 2020 code, National Electrical Code, it moved to Article 100. Prior to that, in 2017, it was in 250.2, which was the definition .2 section, which was specific to Article 250. But it's moved because it's used in more than one article, so that's generally what the Manual of Style for NFPA does. And so it's up to that code panel to make the recommendation to move it under the purview of Code Panel 1. Even though Code Panel 5 still retains the definition, it just gets relocated to Article 100. That's a lot of words to show you something on the screen. So here's what we got. So a supply side bonding jumper is a conductor installed on the supply side of a service or within a service equipment enclosure, or for a separately derived system that ensures that required electrical conductivity between metal parts required to be electrically connected. So it maintains that intimate connection of all metal parts. Okay, so if I dissect this a little bit for the students so you can see an example, and I try to paint you a picture of all these scenarios of where this supply side bonding jumper would be taken care of. So let's do that. So the very first one would be where it says within a service equipment. It says a conductor installed on the supply side of a service. Okay, that's the first one. Got my phones going off everywhere, folks. So that's the first one. What is that? Well, it's very common to use the grounded conductor under 250-142 on the supply side to bond metal parts like metal wireways, gutters that would have service conductors in it, or even raceways that have service conductors. I could utilize the grounded conductor for that application. So if it's in a wireway and I had lay-in lugs, I could bring my grounded conductors, neutral, and lay them through those lay-in lugs, all of them, and then I could bond that wireway. Very common in meter enclosures, for example, to use the grounded neutral conductor to bond that metal enclosure, okay, meter enclosure. So it's very common. So again, in those cases, there really wouldn't be any sizing in that scenario to make those connections if the grounded conductors are intimately in contact with the enclosure. But if I were to make jumpers from those conductors over to it, then of course I've got to size them, and we're going to talk about that today. But typically it'd be lay-in lugs, and where we'd use the grounded conductor on that side. So that's an example on where you would have a supply side of the service where that would take place. Okay. Now that also means that on the supply side, I can make connections to the grounded conductor to other wireways or raceways as well. But it also takes place in the next one. It says, or within the service equipment enclosure. So it could happen inside the service equipment. So I could have a raceway that comes to an enclosure, and then I have a supply side bonding jumper that bonds that raceway if it has to have a bonding jumper, because you encounter things like concentric or eccentric knockouts and impairment of that continuity between the raceway that contains service conductors and the actual enclosure that contains service equipment. So there's ways, and we'll talk about that as we get through them. And of course, the other one is or for a separately derived system. Now, the best way that I can describe this, and I wish I had, I do have a graphic, but I didn't load it, is that I've got a transformer and I'm going from the transformer secondary up to a cabinet with a disconnect in it, right? Because maybe it's a panel board in the cabinet. So that's on the secondary side of a transformer. So typically I'm going to have a supply side bonding jumper that's run from the transformer to that cabinet, just as the example. And whether or not it's a single raceway or multiple raceways, if it's multiple raceways, it has to be sized into multiple raceways in each raceway. Or it could be a non-flexible raceway like EMT, rigid, IMC, and that would serve as a supply side bonding jumper. Of course, if it's a fixed type of raceway metal that you don't do any sizing, but if it's of wire type, then of course you have to size it, right? So we're going to cover all that in this episode here and try to give you a better understanding. So what is other important thing to understand is the function of a supply side bonding jumper. What is it there to do? It's one thing to understand how to make the connections. You're a journeyman or you're a master and you worked in the trade and you understand the connections and the code tells me I got to do it and my instructor tells me I have to do it. But why are we doing it? And it's important to understand the why. Now, there's some 4 bullet points here that we'll discuss each one of these. It kind of will get into the function and answer the why. And I'll elaborate where necessary. But, okay, first one is, oops, too far, is a supply side bonding jumper provides electrical continuity between the supply source, which usually is the utility, and the various enclosures of the service equipment. Again, for the supply side. All right, so that's everything on the supply side. You have typically a transformer, you have raceways, and there has to be some kind of continuity between the two. And a supply side bonding jumper is making that connection. The next one, it says, connects the bonding bushings where used to service grounded neutral conductor in service equipment enclosures. Now, we'll look at some pictures here in a minute, but that's typically where, let's say I have a service and I've got a raceway coming in and it's going to make a connection to the metal enclosure, but I'm dealing with concentric or eccentric knockouts, those little rings that you knock out. And if they're encountered, when you're dealing with services, you have to do something a little more than normal under 250.92 A and B. You got to do something a little bit other than the norm. In other words, you can't just use a lock nut. So I'm going to have to do some kind of assured bonding method. And so all that's listed, and I got a video on that, service bonding basics you need to go watch if you don't understand those concepts. But you got to do something more. And so when you're dealing with an impaired connection like that, then you're going to have a bonding jumper. And that's going to be, if it's on the supply side, it's going to be a supply side bonding jumper. If it's on the load side, it's going to be equipment bonding jumper. But it's on the supply side, then we have to remember that it's got to be something more than just a lock nut. Now, what if it's a knockout and they remove all the rings and it's of the perfect size for the fitting you're going to use? It'd be like a cut hole or a punched hole. If that's the case, then you might be able to get away without the bonding jumper, but you'd have to do something like a bonding lock nut that's different than a standard lock nut, a bonding wedge, things like that. Okay, so it really depends on the impairment of that connection, and you're trying to maintain the integrity, if you will, of that connection between the raceway that contains service conductors and the metal enclosure. Okay, so again, go watch that video on service bonding basics. It's pretty interesting. Now, so where bonding bushings are required, you would have a bonding jumper. And if it's on the supply side of the service disconnect in service equipment, then that's called a supply side bonding jumper. Okay. Next, you get into, okay, we understand the fundamentals, but now we got to understand the function. And what does it do? Item number 3 here says it carries ground fault current from the ground fault that occurs on the supply side of the main overcurrent protection. Now look, if we have a ground fault on the load side, that's why we size equipment grounding conductors, okay? That's why we do all the things we do in 251.22 and sizing based on the overcurrent device. That way it clears the breaker or the fuse and shuts the system down. We have all those rules, and we have a video on that as well that talks about equipment grounding conductors and all that. Go watch that video because that explains that part of it. But we're on the supply side now. Now, when we talk about fault current that can take place on the supply side of the main overcurrent protection, we're assuming that there's some kind of protection upstream, whether it's fuses and at the utility side, that this will clear in that event in order to clear those energized parts. Again, as an electrician, I don't know what's on that side. I just know that what the minimum rules are allowing me, because ground faults the current that's generated because of the ground fault, what happens is it has to get back to the source, okay? The source of where it was created, and that's the transformer. And so I need to be able to create that low impedance path back to it in order to potentially clear any device that might be upstream of my premise. And so that takes me to bullet point 4. And that is, it says, provides a low impedance path for ground fault current to return to the source. Okay. That brings us to a myth, and we'll talk about this myth. I don't have a slide, but it is when people say that current takes the path of least resistance. And my answer to that is there's always a little bit of truth in some things. Basically, it takes all available paths proportional to the path with the lowest impedance, okay, or resistance. So that means that it's going to take all available paths, and the better that you can provide a low impedance, since we're talking AC systems, the lowest impedance path back to the source to facilitate any operation of any potential overcurrent protected device, to clear the circuit and create a safe condition. If we provide that low impedance path, the majority of that fault current is going to travel on that intended constructed path, okay? And so again, but will it take all paths? Absolutely. There are some higher impedance paths that some current will travel on, but the majority to operate and facilitate what we need it to do will take the path of the lowest impedance. And again, the majority of that current would take that path, okay? But I just want to remind you, if you hear anybody ever tell you that current takes the path, or if they're just broad and they say electricity takes the path of least resistance, it's not 100% true. It takes all available paths proportional to the path depending on the impedance of that path, okay? But it does take all paths, okay? All right, so once we understand the fundamentals, we now understand, well, what can constitute a supply-side bonding jumper? What can it be? Now, we're probably all familiar with the wire. We just run a wire. Bonding jumper, the sheer nature of the term jumper makes me think I got a wire, okay? But it's important to know that supply-side bonding jumpers can also be non-flexible metal raceways, or they can be of the wire type, like what we typically will see, copper jumper, that type of thing. So anyway, the point I'm making here is, and I'm going to have to draw you this mental picture again. Typically on the service side, most of it's going to be either non-metallic, where there is nothing to bond on the service side, if it's non-metallic, obviously. Duh. Or it's metal of some type. And if that's the case, then you're going to bond it. Now, if it was a flexible type, then that's not going to work because you can't literally use the raceway that is flexible as a supply side bonding jumper. So on the supply side, usually coming in for service conductors, it's usually going to be rigid, intermediate, EMT, or something like that. But what I want to draw your contrast to is what happens when we talk about the supply side bonding jumper for, let's say, from a separately derived system, and we'll just use a transformer. It goes from the secondary, goes up to a cabinet, okay, with a panel board in it, okay? So in this case, that connection between there, if I were to run EMT, if I were to run rigid metal, intermediate metal, then that would be qualified as a non-flexible metal raceway. And if that's the case, then I would not have to run a supply-side bonding jumper in those raceways with those circuit conductors, all right, those secondaries. I would be able to use the actual raceway because it is non-flexible. Flexible raceways, where utilized, are going to require that you have a supply-side bonding jumper inside with it, okay? All right, so kind of those things to remember about the concepts here. And so whenever you see it now, can I have a flexible conduit that then connects to a non-flexible metal raceway? Sure, but the code's going to require in 25102E that I have a bonding jumper. And again, if it's those scenario, I'm still going to size it based on 25102C. And I'm going to make sure that it's not more than 6 feet in length. Now I can run it in the raceway, or there's an allowance for me to run it outside of the raceway. And I'll show you a graphic on that. We won't get too deep in that one, but that does allow me to do that. And I size it no differently than I would based on the conductors that are inside that raceway if I'm doing that bonding jumper for that raceway. Okay, you'll see a picture in a minute. All right, so, and then lastly, it says right here, service grounded conductors can sometimes also serve as a supply side bonding jumper. Absolutely. That's first saw its allowance in 250.142, which says that I can use the grounded conductor to bond equipment on the supply side. Very common to use the grounded conductor to bond wireways that hold service conductors or meter enclosures and things like that. If service conductors are involved in it, then it is one of the methods that we can actually utilize it and be able to actually bond all those enclosures to the grounded conductor. You got to remember, we're going to do that anyway, even in the service equipment, from the grounded terminal bus over to the raceways as well. In an example I'll show you. So why would you not be able to do it upstream? One little tip I will give you is that I've had people, for example, ask me questions. They say, well, what if I've got 4 raceways in parallel and I've got 4 sets of conductors coming through a wireway, and maybe I had to have a wireway because I needed the room to get conductors through something, meter or whatever it is. And I'm coming in there and I want to bond that wireway to that grounded conductor. Can I ground it to just one of them? And the answer is absolutely not. Okay, you need to ground to all of them. Okay, so they all would have to go through the lay-in lugs, okay, and make that connection, okay? And of course, you make your connections in accordance with 250.8, and usually it's drill and tap, or you have 2 threads, constant contact type thing. But there is a methods that you need to be aware of to do that, okay? Okay, so we got all that out of the way. Now, talking about sizing. So remember now, we're going to do supply side. We're not doing load side. That'd be 250.102D. We're on supply side, okay? These are service conductors. That's what we're talking about. If service conductors are in the game, then this is how you're going to bond on the supply side. If you're dealing with feeders, then it's a little different. Equipment bonding jumper or whatever on the load side. Okay? We're on the line side or we're on the supply side. Please distinguish the two. All right. Now, here's where I'm going to keep it really simple, and I'll probably explain this right now, and then it makes the rest of this not necessary. Okay? Let's draw a picture. I'll make it clear. I have a switchgear. And I have an open bottom. And I'm coming up from the open bottom with 1 raceway. That's it. Rigid metal conduit. Simple. It's coming up. And I have a 3-phase. And it's coming up, and it's a black, red, blue, and a ground. And equipment, grounded conductor. And so it's service conductors. And so I've got a phase A, phase B, phase C. Now, I take the largest ungrounded conductor of the set. And so A, they're all 500 kc mil. So I take A. It doesn't matter. A, B, or C. It doesn't matter. So I take A. It's 500 kc mil. Now, I've got to make it. It's an open bottom. I've got to bond that raceway because it contains service conductors. And the code tells me I have to do that. So how do I size it? Well, remember, it's based on the size of the largest ungrounded conductor in that raceway. There's 3 500s. I only need to use 1. Okay, phase A is fine. So I would be 500 kc mil. So I go to 250.102C1, which ultimately is going to tell me to go to the table. So that's what we're going to do. We're going to go to the table. So as you see here, I'm dealing with the single largest ungrounded conductor in 250.102C1, and I'm dealing copper, and I come down, and what you'll notice is that we're in the column where it says, and I don't know if you can see it or not, so I'll try to highlight it. We're right here. We're over 350 through 600 because we're at 500 kc mil. We're just using one of the phases, okay? Now, because it's not parallel, there's only one, and it says I use the size of the largest ungrounded conductor, okay? Not conductors, conductor, all right? So here it says I need a 1/0, all right? So in this case, I got 1 raceway. I got 1 supply side bonding jumper, and it's 1/0. All I do is make sure I got the right lug that can handle a 1/0. Make sure everything's listed for the application for grounding and bonding. And I make a connection from the grounded terminal bus over to that raceway. I'm done. That's it. Just that simple. Now, here's where you don't see people explain it because they assume you already know this. What if I'm in the same scenario and I have a trade size 6 or 5, whatever it is, and I've got, whatever size, right? And I've got 2 sets of 500 kc mil. So I got 2 A phases, 2 B phases, and 2 C phases, okay? And that's what I'm dealing with, okay? And of course, I got my grounded conductor as well. So if I'm dealing with this service now, how do I do that? Well, let's go back to the code because here's what you don't see people talk about. Right here. Notice right here it says at this point we got into what's called equivalent area for parallel conductors. It doesn't matter that they're all in one raceway. They're still parallel conductors. So in this case, we're dealing with two 500 kc mills. So you add the two together. Two phases, because remember when we do paralleling, phase A, phase B, phase C, we got two conductors, two sets. All we're doing is replicating a single conductor, but we have to parallel it because we don't want to run a big conductor. Okay, it would be on bigger raceways. We get to parallel. It's a beautiful thing, paralleling. But you have to meet all the characteristics. Same length, same material, same conducting material. Copper, you can't mix copper and aluminum, obviously. You know, that type of thing. All the characteristics are the same under 310. Then we can do what's called paralleling. And it's basically joined at both ends, and it replicates a single conductor, even though it's parallel, because it's joined at both ends, and the current will divide evenly if all the characteristics are the same. That's the concept, right? All right, so when everybody follows that, that's what it's supposed to be. All right, so if you look at that and we go back to the code, then in that case, two 500s, that would be equal to 1,000 kc mil, right? So here we're over 6 through 1,100. And in that case, it would be a 2-aught. So, pretty simple, right? Easy stuff. So even though I've got parallel sets in a single raceway, I'm going to have a 2-aught supply side bonding jumper. Make sure I got the lug can handle it. Make sure I terminate it right. Everything's torqued right or done right to meet the terminal limitations stuff. All that's done. Happy, okay? Now, here's where people get confused. When I have two or more raceways, and it really shouldn't be confusing, because when you learn the concept I just said, it seems to make better sense now that we have two or more. But I get this question a lot. So now I've got two raceways. So now we're going to get into, and I'm going to show you some examples of how you do it. And then you're going to say, I get it, Paul. You made it crystal clear. So let's go back to the presentation now, and let's kind of look at an example. So here's an open bottom switchboard. All right, and ignore me. I'm blocking some text, but it's not necessary to the text at this point. Just look at the graphic with me. And you'll notice I got 4 raceways. And if I got a 500 kc mil in each raceway, that means I've got 4 sets, okay, and I'm dealing with, okay, ABC, 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 ABC in this example. Now, I've got the grounded conductor in each raceway. Now, the reason the ungrounded aren't shown because we don't want to clutter up, and I don't need to show those terminations because I can tell you what's there, okay? So what we've got is we have a 500 kc mil set here, set here, set here, and set here. So when you have 2 options here, you can run what's called a single supply side bonding jumper like you've shown here where you're looping it through, or you can run this option where you have individual supply side bonding jumpers as you see here on the screen, okay? Now, let's look at this one. Now, this one can be problematic because when you have a single conductor like this that's connecting all of them, then you have to take up the cumulative amount of each one of the largest ungrounded conductor in each raceway in order to be able to size this supply side bonding jumper. So if you want to do this method, there's some problems in a sense that you got to make sure the lugs are going to be able to handle this larger conductor. Well, what size are we doing? So we need to know that. So we said it was 4 sets of 500. So we'll just take any phase, take A, because they're all the same size anyway. And I'll show you another example where that would be different. Phase A, they're all 500s. So I got a 500 here, a 500 here, a 500 here, a 500 here. No, you don't add up all 3 of the phases. You just take the largest of each raceway. It's 500. Phase A. You could use B or C. It doesn't matter. In this case, 500 plus 500 is 1,000 plus 500 is 1,500 plus another one is 2,000. So now we're at 2,000 kc mil or 2 million circular mils, however you want to do it. Okay, the K in kc mil stands for 1,000. The C mils is circular mil. Okay, so we abbreviate it by talking. And then back in the day, it used to be 2,000 MCM, but we don't do that anymore. The M was also 1,000, but now we say K for kilo, 1,000. So just, old timers, you might hear them say MCM. Okay, I'm not even old enough to say MCM. I've always said kc mil. Anyway, I digress. I have ADD bad, if y'all hadn't got that by now. All right, so if you want to do the single, what do we have to do? So now we got to go to the code. So the code says, what happens if we have over 1,100? And in our case, we do have over 1,100. We have 2,000. So again, this is 1,100. This is 1,100,000 circular mils, okay, or 1,100 kc mils. And we know that because it talks about it right here in the kc mils, and we know what we're dealing with. And anything here, 3/0 and less, that's American wire gauge. Once you start getting over that, you start getting into kc mils, okay? So anyway, we're larger. than 1100 kc mil. We're 2000 kc mils, right? All right. So in this case, we look over here and it says, well, you got to look at the notes. Well, we're going to use note 1 for our application. And so here's what it says. If the ungrounded supply conductors are larger than 1100 kc mil copper or 1750 kc mil aluminum, the grounded conductor or bonding jumper, and that's, of course, that's what we're sizing here, shall have an area not less than 12.5% of the area of the largest ungrounded supply conductor or equivalent area for parallel supply conductors. Okay? And of course, it says the grounded conductor or bonding jumper shall not be required to be larger than the largest ungrounded. That would be pointless. If you don't want to do the math, then you literally make those conductors the same size as your ungrounded conductor and you just walk away. And why would you do that? But you could. It doesn't have to be larger than that. But let's get to what you'd have on an exam or in the real world when we're sizing these supply side bonding jumpers. Okay, so we know we're over 1100 and we're at 2 million. So then we have to get our calculator and do this. So we got our calculator and I'm going to get mine all jacked up here and say, okay, well, I've got 2 million kc mil. Excuse me, 2 million circular mil or 2000 kc mil. So I'm going to turn that, or I'm going to take the 2000, all right, times 1,000, just as that's the way I usually do it, even though I know what it is. That's 2 million circular mils, right? Now, once I have those 2 million circular mils, I'm gonna do that times, I'm gonna say divide, times 12.5%. So in my calculator, let's go times 0.125. And that is 250,000, I don't know if you can see that, there it is, 250,000 circular mils. So we don't need to go to Chapter 9, Table 8 to look for that. We know that 250 is 250. Now, if the number was a weird number between there, like 320,000, whatever, then you would go to Chapter 9, Table 8, and you go down and you find which one you would need. But you really don't even need to do that either, because if you know it's 3 something, you either got to be 350, or if it's over 350,000 circular mils, then you have to go up to 400,000. So it's pretty simple at that point. So in our case, we needed 250 kc mil. So if that's the scenario, let's go back to the presentation. If we were doing that, we're going to be forced to have a single 250 kc mil as this looped through single type of supply side bonding jumper. Now, some of the things that might come into mind that I worry about is whether or not these lugs are going to handle it. Okay, lugs have sizing limitations on them, the range that they can be at. And so that might be a problem. Or I might have to go to some real expensive lugs and it kind of defeats the whole purpose. So why would I do that? But you do have that option. That is one option, okay? And that's what it says right there behind my head, saying that's one of the options you have. But most people aren't going to do this option. They're going to use a second option, and that is to run the individual supply side bonding jumper. This is the option that most people will do. And it's going to result in a smaller conductor, and it's going to be more compatible with the lugs that are out there. So in this case right here, it's pretty simple. You treat each one of these raceways just like we did as a single raceway. In other words, it's based on the size of the conductors, service conductors that are inside of that individual raceway and the largest. So again, you would choose either A, B, or C. If they're all the same size, then it's 500 kc mil. And so for that one, it would be, I think earlier we saw it was a 1/0. So I need a 1/0 supply side bonding jumper for each one of those raceways, okay? And the reason we're bonding those raceways again is because they come into an open bottom, and those raceways contain service conductors, and the code requires us to bond under 250.90 and all the methods under 250.92 A and B. It requires us to bond those raceways, right? So we did it, and we sized it that way, and we used a bonding bushing with a jumper on it over to the grounded terminal bus. Okay, that's simple, right? So again, you have the options to loop through, and it's going to result in a larger conductor. Why would you? But you can if you want. And then, of course, you have the option to do individuals like this. Okay. Now, the only reason I think somebody ever do this is maybe you don't have enough lugs on your grounded bus and you're in a pinch and you have some bigger conductor available and you luckily have lugs that can handle the size you're dealing with. Good. You're gravy then. But usually this is the kind of scenario that we're dealing with. Okay. Now, I'm going to bring a weird scenario in for you because I like to give you weird stuff. When you're paralleling, it only requires that, say, phase A, B, and C have to have the same characteristics when you're dealing with paralleling applications. So phase A could be copper conductor. Phase B could be aluminum conductor. Phase C could be copper-clad aluminum. As long as all the conductors of that given phase have the same characteristics, okay? Same length, same type of installation, all those type of characteristics, all those things are terminated in the same way. All of those characteristics are the same conductive material. All of those phase A are copper, for example, blah, blah, blah. If you meet all those requirements, you're good to go. Now, if you ever run into a weird scenario, I'm just tell you it's a weird scenario, whereas you have an A, B, and C in each one of these raceways, and let's say your A and B are 500 kc mil, and C is 600 kc mil. I don't know why you would do that, but I just want to point it out. If you did, I don't want people to, I like to give you as much as I can give you. So if that was a scenario, each one of those raceways will have an A, B, and C, and the C will be a 600 kc mil in each one of those raceways. So how do you apply this rule for that? Again, it's the largest conductor in the raceway. So in this case, you're going to jump to C because C is 600 kc mil. So you do everything you did before exactly the same. It's just you're going to base everything off the fact that you're going to use the largest conductor. So you're going to take the 600, 600, 600, 600, add them together. Okay, if you're going to do a single one like this right here, you add them all together. And in that case, it was, we'll do that and see if it changes anything. So let's do 600, and that's 600,000 times 4, and that's 2,400,000 circular mil. And we'll do that since we know we're still at that point going to be in the 2.5%. So if we were doing this, then we do that times 0.125, and that would be a 300. So I'd have to run a 300, whereas the 500 kc mils would allow me to run a 250. So you see how that makes a difference. Now, what about the scenario in right here? If that was the same weird scenario, if that ever happened to you, then again, you ignore the 500s, and again, you're taking the largest ungrounded conductor in that raceway. In this case, it's phase C that was 600, so you use 600. Now, in our case, it wouldn't change the size because if you go to 250-102, you'll see that it doesn't matter. And I'll go back here. You'll see here that it's over 350 through 600. So when it says through 600, it means it includes 600. And it's still a 1/0 copper for that as well. So it didn't change anything in our scenario, but I just wanted to throw that out to you in case you ran into some scenario like that. Okay. Well, and again, the only other thing that I want to add here is, I'll go back to the presentation, is in many cases, you might even have supply side where you're having to make a jumper. All right, so typically, let's look at it this way. You can have a supply side bonding jumper. Typically, it's ran inside of the raceway, but there are allowances where it can be outside of the raceway. And so in this case, you see a flexible conduit, and then you see a fixed non-flexible at the bottom of the screen. In order to maintain the integrity, if they were using the fixed metal, or I should say the non-flexible, like an EMT rigid or IMC, and now they impose into it a flexible type, then you have to maintain the integrity of, if you're using that EMT rigid or IMC, the lower part down there, then you're going to have a supply side bonding jumper. It can be inside or outside. In this case, they're running it outside. Okay, that is allowed as long as it's not more than 6 feet. And it's sized the same way based on the conductors that are in that raceway. And this is typically what you would see as an example of that scenario. So all of this is covered in 250-102E, and it's pretty simple. Just make sure you follow the basic rules. And remember, sizing pretty much stays the same as we did in 250-102C, okay, in this scenario. So again, great information. It was a great question that was presented. Hopefully you got something out of that in this episode. Again, don't make it overcomplicated. It should be simple concept to do. Again, treat parallels as parallels. Treat singles as singles. Don't overcomplicate it. And remember, we're talking supply side. We'll have another episode that shows you what to do on the load side, but the long and short of that is, again, you size everything based on the size of the overcurrent protected device on the load side for equipment bonding jumpers and things like that. And that's going to send you to 250-122. And we got a video on that. So hopefully you got something out of it. Also, a shout out. We go live. Electrician Live podcast and vidcast goes live January 4th, 2020, whenever you're listening to this, if it might have already passed. But that's when the live shows start that you can call in. As you see on the ticker above, you'll be able to call in using Skype at Master the NEC as the ticker. And you'll be able to call in and interject with us as we talk all kinds of topics about electrical. So it should be a real neat and interesting show. I look forward for you to join in on us at electricianlive.com. as well as on Master the NEC's website. So till next time, folks, if you need anything, remember, you can email us at info at masterthenec.com. I'm more than happy to answer any of your electrical code related questions, or we can just chew the fat on all things electrical. It's up to you. Till next time, folks, stay safe. God bless.